Hello guys, today I am here about to discuss about PN junction diode. These are the contents we discuss in this section. First, what is PN junction? In a piece of intrinsic semiconductor, if one half is doped by p-type impurities and another half is doped by n-type impurities, the PN junction is formed. The plane divided into two halves or zone is called PN junction. As shown in the figure, the n-type material has high concentration of free electrons and p-type material has high concentration of holes. Therefore, as the junction, there are tendency of free electrons to diffuse over the p side and the holes to the n side. This process is called diffusion. As the free electrons move across the junction for n-type and p-type, the donor atom becomes positively charged. Hence, the positive charge is built the n side of the junction. This is the figure of PN junction diode. Here we have the n-type material and p-type. This is the symbol of the diode. It has a positive terminal and negative terminal. The negative terminal is called cathode as K. Anode, the positive terminal is anode as A. The arrow shows the conventional current flow. The free electrons that cross the junction uncovered the negative acceptor ions by filling the holes. Therefore, the negative charge is developed on the p side of the junction. The net charge on p side prevents further diffusion of electrons in the p side. Similarly, the net positive charge on the n side repels the hole crossing from p side and the n side. Thus, a barrier is set near the junction, which prevents the further movement of charge carriers, that is, electrons and holes. The magnitude here, the potential barrier is formed. The potential barrier is also known as a junction barrier or diffusion potential and contact potential, that is V0. The magnitude of the contact potential V0 varies with doping levels and temperature. The V0 is 0.3 volts for germanium and 0.72 volts for silicon. Here the energy band is shown. The energy band is shown. Here we consider the conduction band and the valency band. This is the Fermi level. This is the Fermi level, and this is the n-type material and p-type material. Here we has energy level. These are the energy band diagram. Forward based junction. When the diode is connected in forward condition, a negative voltage is applied to the n-type material and the positive voltage is applied to the p-type material. This shows the forward bias of the junction. In this, internal voltage becomes greater than the value of potential barrier, approx 0.7 volts for silicon, 0.3 volts for germanium. The potential barrier opposition will be overcome and current will start to flow. This is because the negative voltage pushes or repels electrons towards the junction, giving them the energy to cross over the combined with the holes being pushed in the opposite direction toward the junction to the opposite voltage. This results the characteristics curve of the zero current flows up to this voltage point is called knee of the static curve, and then the high current flow through the diode with little increase in the external voltage. This is the forward characteristics curve for the junction diode. The figure shows the forward characteristics and the flow of current voltage within the forward bias. The application of forward bias voltage of the junction diode results in the depletion layer becomes very thin and the narrow, which represents a low impedance path through the junction, thereby allowing high current to flow. The point at which this sudden increases in current takes place is required on the static VI characteristics as about nil. The figure shows the characteristics of the forward bias. The PN junction diode under the reverse bias. The reverse bias means the P-type material is connected to the negative terminal and the N-type material is connected to the positive terminal. That is said to be a reverse bias condition. The positive voltage applied to the negative material attracts electrons towards the positive electrodes and away from the junction, while the holes in the N-type and also extract away from the junction towards the negative electron. The net result is that depletion layer grows wider due to a lack of electrons and holes and present a high impedance path, almost an insulator. The result that a high potential barrier is created, thus preventing current from flowing through the semiconductor material. The figure shows the reverse bias of the PN junction diode condition. The reverse bias condition curve for a NIC junction diode. The figure shows the reverse bias characteristics of the PN junction. The reverse bias has the breakdown region. This is known as Zener breakdown. Sometimes this breakdown has partially applications in voltage stabilization circuits where a series limited resistors is used with the diode to limit the reverse breakdown current to a preset maximum value, thereby proceeding a fixed voltage output across the diode. These type of diodes are commonly known as Zener diodes. In this, in this reverse voltage, we have this diagram as shown in the figure. These are the combination of forward characteristics and the reverse characteristics, that is known as VI characteristics, VI voltage current characteristics and their temperature dependence. Here the knee voltage are there, that is known as PF, forward voltage, forward current, forward bias region, avalanche breakdown. At this point we have the breakdown, that is known as avalanche breakdown. This is the breakdown region and the reverse bias region is this, and the breakdown voltage, reverse current. These are finally the characteristics of the PN junction diode. Thank you.